Welcome back to the final video in the Chapter 8, Section 3 video series. These are the nth roots of complex numbers. So today we're going to learn how to find roots of complex numbers. You should feel really comfortable with Moivre's theorem, trigonometric ratios, and you should feel good about graphing angles in the coordinate plane. This is actually a very, very cool lesson. So we're also going to learn what an nth root is. To warm up, let's use Moivre's theorem to find the third power of negative square root of 3 minus I. Take a moment, pause the video, restart when you're ready to see the answer. I will show the answer in 3, 2, 1, now. Hopefully you remembered Moivre's theorem. If you do not, take a second and write down the formula on the bottom right. We're going to use that a lot today. In our previous lesson, we used the fantastic Moivre's theorem to calculate the powers of complex numbers in polar form. So recall our example, 1/2 plus 1/2 I to the 10th is 1 over 32 times cosine 5 pi over 2 plus I sine 5 pi over 2. In this case, we raised a complex number to a power. Z to the 10th gave us W. But what if we need to go the other way? We need a way to take the expanded form of a complex number and take the nth root. So to do this, we use an adjusted form of Moivre's theorem. Let's take a look at that now. Suppose you have a complex number. I'm laughing because I say this in every video. A complex number Z in polar form. Then Z has n distinct nth roots, which can be found using the following formula. Now, just to give you an idea of what this formula means. WK is the kth root of Z, okay? Now, each of the roots has the same modulus, so we can calculate one modulus and apply it to each root, but you can see that the arguments change by the same amount for each one. Similar to how things work in the unit circle, we're constantly cycling our angles, same thing here. So, and if you plot this root in the coordinate plane, complex plane, they're going to be evenly spaced around a circle with a radius equal to the modulus. You will get to see this, and it is very cool. In our first example, we need to find the sixth roots of Z equals negative 64. So let's start off by finding our A and our B. A is negative 64, and we have no imaginary part. So if we need to put this into polar form, we've got a pretty easy calculation. Our R is going to be 64, and our theta is going to be pi, because the tangent of the arctan of 0 is pi. So it's in polar form. 64 equals cosine pi plus I sine theta. Now, since all of our roots are going to have the same modulus, I'm just going to calculate my modulus. So that I take my R and I raise it to the 1/6 power because n is 6. So my modulus is 2. Sorry, the sixth root of my modulus is 2. So we have a generalized formula that we're going to use. So you can see I filled in basically my nth root of R and n. And now what we're going to do is take k and cycle it all the way through from 0 to 5 until we find all of our roots. I'll show you on the next slide. So there's my formula, my starting formula. And I start with k equals 0. I can calculate each root. Okay, one at a time. If k equals 0, W naught equals square root of 3 plus I. I'm plugging in 0 for k. When k equals 1, W1 equals 2I. When k equals 2, negative root 3 plus I. When k equals 3, you can see how your k keeps changing. We're just changing it as you go through. Negative root 3 minus I. And we'll continue to do this until we get to k equals 5. Remember, 6 roots, we start from 0, so 0, 1, 2, 3, 4, 5. Okay? So now we have our roots. Let's take a look at what they look when they're graphed. I'm going to graph them one at a time. W naught, root 3 plus 1. W1, 2i. W2, negative root 3 plus I. W3, negative root 3 minus I. W4, negative 2i. And W5, root 3 minus I. This is a circle with a radius of 64 to the 1/6 power, which is 2. And these are all evenly spaced by 2 pi over 6, which is pi over 3 apart. It's pretty cool, right? Our formula can be used for angle measures that are also in degrees, but we just have to make a change. So instead of 2 pi k, we'll use 360 k. Same process, okay? Let's try an example. In example 2, we need to find the 3 cube roots of z equals 2 plus 2i. Okay, so a equals 2 and b equals 2. Take a second and see if you can calculate your radius, your argument, and put it into polar form. All right, I'm going to show my answers now. All right, so we have a pretty straightforward polar form. Things get a little bit tricky when we calculate the nth root of r. We're going to need to use some fancy math. So we need to rewrite 2 square root 2 as 2 times 2 to the 1/2 power. Then we combine, we have the same base, so we get 2 to the 3/2 power. Then we use the power property and multiply our powers together to get 2 to the 1/2, which is the square root of 2. And here comes my general equation. I am going to use this to find all of my powers of k. Starting with k equals 0, we're going to calculate each root again. Remember, we're expecting 3 roots, so we're going to stop when k equals 2. So when k equals 0, we have this gnarly answer. Just remember, you don't have to use decimals, but it is easier when you need to graph them, okay? For k equals 1, similar example, you can see I'm changing k each time. And then for k equals 2, I get the following answer. So we're going to graph these three. I would say you'd have trouble graphing if you didn't have this in the decimal form on the right. So I'm going to throw these on here, W0, W1, W2, and guess what? Circle, radius, square root of 2. Oh, and they're evenly spaced, 360 degrees divided by 3 because these are cube roots. Okay. For our final example, we have to solve the equation x to the 6, z to the 6, plus 64 equals 0. Subtract 64 from both sides, you get z to the 6 equals negative 64. Guess what? We found these solutions already in example 1. Here are my 6 sixth roots of negative 64.